Already started.
Excellent. All right. So one moment and we will get started. All right. So thank you all for coming to this specially scheduled Origin seminar talk. Today we are pleased to host Dhruv Muley, who is entering his fourth year as a PhD student at the Max Planck Institute for Astronomy in Heidelberg. His research focuses on developing and applying numerical hydrodynamics methods to the study of protoplanetary disks. And today we will hear about a powerful new tool to investigate protoplanetary disks. So Dhruv, take it away.
Thanks, Allison, for the very kind introduction. And yes, as you said, today I'll be talking about three-temperature radiation hydrodynamics that I've implemented into PLUTO hydro code, which I've used over the course of my PhD to investigate protoplanetary disks. This work was done in collaboration with postdoc David Merlin-Fuchsmann, one of the main developers of the PLUTO code, and my supervisor, Hubert Clark, at the Max Planck Institute.
Dhruv, could you share your presentation screen, please?
Oh, can I? Is it not being?
No, this is just.
What do you mean?
Oh, sorry.
I am sharing screen.
You are sharing screen. Let me fix this.
We'll see, yeah.
That was my fault. I apologize. We're fine. Continue.
All right, let's carry on. So just okay, so I think just to start out, this is a very theoretical program of research, but I should give some observational background and motivation because that's really where everything is rooted. So just to start off, let's take a look at these spiral structures that you see in TW Hya. These were observed by Richard Teague and team in 2019. On the one side, you see thermal spirals, temperature versus some background axisymmetric model temperature. You can see a clear wound pattern. And then also in the velocities, you can see there are some that there appears to be also spiral or annular sort of pattern, deviations from some simple axisymmetric background that they assumed. Now, this can also be seen in a system known as CQ tau observed by Sebastian Wolfke et al. In 2021. You can see they attempted various fits to, I think what's shown here are the kinematic spirals, and some of the fits are also temperature spirals. So these spiral structures that you see in gas, 12CO, 13CO, C18O, among others, are examples, one example of substructures. Now, if you turn your attention to dust, for instance, the millimeter dust observed by ALMA, looking at the very well-known D-sharp program, you can see they observed many disks with, in high resolution, a lot of annular substructures. And now turning our attention just to a different waveband, near-infrared scattered light, observed, for instance, with VLT sphere or with Gemini, you can see observations of SAO 206.462, HD something something telephone directory. You can see there are these clear two-armed spirals, and such features have also been observed in many other systems. For instance, MWC 758. Now, I think there's, in connection with these, there's been a program of theoretical research going back decades, which suggests that substructures, such as those I mentioned, are the result of disk-planet interaction. Now, the way the picture goes is you have planets exerting torques on disks at the so-called Lindblad resonance, basically where your planetary orbital frequency is equal to some multiple of, I think, I'll say Doppler shifted force equals basically the frequency at which you see material next to you in the rotating frame is equal to your own frequency, more or less. And this was a theory developed by Goldreich and Tremaine in the late 70s. I won't go into details about this, but the idea is you have some gravitational perturbation in your disk, but because it's a gas disk, these gravitational perturbations will propagate as sound waves. The disk, these sound waves deposit angular momentum, and they open gaps. This can be responsible for spiral substructures such as these, and then the gaps which are created over time can be responsible for the annular substructures such as these. Now, yeah, this is the picture, but more recently, there's been hydrodynamical work that has helped to enrich and modify this. For instance, some recent work by Alexandros Ziampras et al. 2023 has shown that if you include full radiation hydrodynamics in your simulations, it can affect the observational appearance of these spirals. And if you look at the paper, it also affects the final gap shape, which results sort of in multiple gaps, which are connected to they connect to some of the D-shelf observations. And if you look at work, for instance, by Jahan et al., where they parameterize the impact of gas grain collisions, they find that these are actually the critical regulating factor for, I think, thermal relaxation in the upper atmosphere, which is where your 12 CO and to a lesser extent 13 CO are observed. And because these gas grain collisions, affect the thermal physics in the upper atmosphere, they basically are responsible for the appearance of thermal spirals. Again, this is what I was talking about from Ziampras et al. It affects not only the spiral structure, but also the eventual gaps and rings you create. And then here is basically the with and without gas grain collisions, what sort of cooling time you get. And this is, I think, a log 10 of the cooling time with respect to your orbital time. If you have a much longer cooling time than your orbital time, then you can see thermal features. If you have a much shorter cooling time, then basically you relax your background temperature on a timescale much faster than any sort of planetary or dynamical effect. Now, what all this research points to is that in order to meaningfully reproduce increasingly detailed observational data, you need to account for both radiation transport and gas grain collision at the same time in your hydrodynamic simulations. And just stepping back a little bit, looking at the problem, the way disk illumination works in essence is you have radiation from the star, strikes the disk midplane. It tends to get thermalized at the disk midplane. Basically, you have wavelength of the stellar temperature. Basically, it follows the temperature of the stellar. The spectrum of the stellar temperature strikes the surface, and then there's a new equilibrium temperature there. The spectrum changes. Effectively, your frequency integrated opacity changes. Some of it escapes, some of it gets bounced around the disk midplane. And the interesting thing here is, like I said, gas contains most of the mass in the disk and heat capacity upwards of 99%, but dust supplies most of the opacity. So gas interaction with radiation has to be mediated by this gas grain collisional coupling, which in the midplane can be very, very fast. But in the upper atmosphere, as we saw in the previous graphic by Jahan et al., can be rather slow. So I think just very briefly, here are some of the equations that we're going to solve. Gas grain collisions, basically there's a coupling time. This is essentially proportional to the temperature difference. Gas and dust opacities, but like I said, the gas opacity is much smaller than the dust opacity. And now, how do we account for this in hydrodynamical codes? Now, this was something I developed earlier in the course of my PhD. So radiation hydro codes, as we know, already exist. And then you also have codes that can account for cooling on some time scale, and you can add in some parameterized cooling to account for the gas grain coupling. But in order to really, the advantage of radiation hydrodynamics is that it allows just the disk heating and cooling to respond in real time to changes in the disk structure. For instance, if you open up a gap in your disk, this will expose some part of the outer gap edge to more direct starlight, so you get a hotter gap, outer edge, you get some puffing up, for example. So having this real-time interplay is important, but also having interaction between gas and dust, the gas grain collision, is important, especially in the upper atmosphere when you care about observational signatures like thermal spirals. Did you have a question or something?
Yeah. Can you just explain the notation there? What are the deltas? They don't look quite like they're partial derivatives.
Here?
Yeah. No. Well, I'm seeing them in the radiation equations. got the delta before the divergence and then also on the right-hand side.
Delta before, I'm not.
The coherency, the speed of light.
Sorry.
C hat.
Okay,
So
sorry,
this is
check
like-
my glasses.
I think this is, okay. So, so this is like I think a reduced speed of light. Basically, yeah, you don't want to handle the full speed of light in this problem, otherwise you're very current limited, and this makes it less bad, as long as this reduced speed of light is faster than any in the problem. We can talk more about this later. But yeah, basically, the way I implement this in a radiation hydro scheme is you have a hydrodynamic step. I will not talk about this anymore. Then you have a radiation step, which is explicit, which is used to transport radiation. Also set the radiation pressure tensor, which sort of sets how the flux evolves. And this is something I inherited from the M1 scheme that's already in PLUTO. In effect, it's like a continuity and momentum equation for the radiation energy and flux. I guess the advantage of this M1 scheme is that rather than assuming, for instance, just isotropic diffusion of radiation, which is often done, you interpolate between optically thin and optically thick regimes. So if you have, for instance, like a vortex in a disk that's casting a shadow behind it, M1 can account for this. Some diffusion type scheme, flux limited diffusion, cannot really account for shadowing. And then now I think this is really where my contribution came in. So this implicit radiation scheme, it incorporates the terms for gas-dust energy exchange, which I flashed briefly earlier, absorption and emission of radiation by gas and dust, opacity, and then of course the stellar irradiation. Now this part was implemented explicitly, so you just sort of directly evolve it. And then this part is implemented implicitly, so basically the update depends on the quantity at the end of your time steps. So in general, there's no way to analytically solve this, and you need some kind of iterations in order to, and you have to iterate until convergence. And we use a sort of multi-dimensional Newton-Raphson scheme in order to do this. But I think, yeah, this is all very technical detail. I'll step out a little bit to the numerical tests, just basically 0V test purely of this implicit part. There's no transport going on here, but basically it works. And for this test, you had dust and gas at separate temperatures, and then radiation at a separate temperature much higher. So this problem is radiation dominated, but yeah, over some time, dust and gas relax to the same temperature. They become coupled to each other. And then the dust gas mixture together sort of heats up to the radiation temperature. And yeah, your numerical solution is in pluses, analytical solution is solid lines, and it works. Now, let's take a look at some applications, enough about the details of technical details. So one problem I applied this to, as I said right here, is the study of planet-driven spirals in protoplanetary disks like TW Hya. So one thing before we move on, would you be able to tell me maybe like 30 minutes, 15 minutes, something like that?
Yeah. We're at 15 minutes so far.
Okay. So to study protoplanetary disks, I use the 3T scheme where, as I mentioned, you have separate temperatures for your gas, your dust, and your radiation, and they all interact. And the coupling is computed via this Newton's method scheme that I mentioned earlier. And then you have two temperature radiation hydrodynamics, which is the same thing, but I assume that there's perfect coupling between the gas and the dust. So in effect, your cooling time in the upper atmosphere becomes very, very short. And then there's a so-called beta cooling, where you parameterize, I mentioned this, you parameterize it based coupling time based on optically thick and thin radiation, as well as gas gradient collision rates. But at the same time, your background temperature is fixed. It doesn't respond to changes in disk illumination. And then finally, there's the locally isothermal approximation, where in effect, you're assuming that in each grid cell, the temperature there remains the same for all time. Now, in each case, I guess we computed some background temperature based on some, I guess, iterative radiation calculation. Those of you who've done radiation, like just pure radiation transport codes for disk modeling, might have done something like this exercise. So we did something like that. And then from that, we computed, I think, yeah, you can put this self-consistently into the 3 temperature and 2 temperature codes, but for beta cooling, you can get out some gas grain collision timescales under certain assumptions of the grain size distribution, et cetera, et cetera. Obviously thick and thin cooling rates, and then you plug that into your beta parameters. So it's spatially dependent in this case. We tested 3 different planet masses, Neptune, which is a so-called subthermal planet. So in effect, I think its hill radius is much smaller than the scale height, and then Saturn hill radius is about the scale height. Jupiter mass hill radius is greater than the scale height. 2-order unity, there is some factor there. And then we tested actually, interestingly, cases with and without planetary accretion luminosity. So not only do we test luminosity from the star, we also inject a source of heating from the planet. And just to see the spiral development, we ran it to 10 orbits. So our results on thermodynamics, we fixed just a Saturn mass planet for this test. For the locally isothermal test, which was historically common in these hydro simulations, the velocity and density perturbations are overstated. And inherently, like I mentioned, fixed temperature for all time, you cannot account for any temperature changes. If you do beta cooling, you get a reasonably accurate gas temperature and density and velocity perturbations. But like I said, you cannot account for any changes to the structure of the disk. So when you go to higher mass planets that really change the shape of the disk, or when you have accretion luminosity, this will become problematic. And then with 2 temperature, you are fairly accurate in the midplane, but then in the upper atmosphere, but then in the disk atmosphere, you end up with this problem that you can see there's blue. There are no thermal spirals in the gas. And this becomes a lot more apparent when you go to higher planet mass, the fact that there are no thermal spirals. And becomes more apparent in a 2D cut, which you'll see shortly. Now, I guess some of the results for spiral structure. Just briefly, I guess I can talk about buoyancy resonances, which are another kind of spiral which can appear in disks. The Lindblad spirals generally follow linear theory in the midplane. They deviate at higher altitude. Buoyancy spirals are actually fairly weak. They're only really visible here because I tested showed vertical velocity and changed the color scale. But that's because the coupling time is generally shorter than your dynamical time. So it's shorter than the local, I think, buoyant frequency. So these spirals get washed out by the, I think, effective coupling rate before they, get the chance to show up. But this is, of course, not a universal truth. If you look at the parameters from, say, Jahan et al. 2021, if you have a disk which is highly evolved with well-settled grains, you would see something like buoyancy spirals because your coupling times would be longer. But in this case, our 3-temperature scheme can only account for grains that are kinetically well coupled to the gas that follow the gas. So you don't see it, and you need a different size distribution. Yes?
Can you, I don't know, supposed to explain that more. I mean, usually, right, buoyancy is right, strong in the isothermal, right. Strong in the adiabatic case of slow cooling. So here you're saying, oh, because this fast rate gives you fast cooling and behaves more isothermally. Yeah, more or less. I think your cooling time is just shorter than your oscillation time. And now, here's what happens when you vary. So now I've just gone to 3 temperature and started varying my planet mass. If you go from left to right, increasing altitude in your disk, you go from top to bottom, increasing planet mass. Now, I think for those who've done this before, a lot of this stuff is well known. You get bigger, stronger spirals for more massive planets. You also get a bigger, I think, circumplanetary region, circumplanetary flows when you have a higher mass planet because the hill radius grows. And so the radius of gravitational influence on the disk of the planet really grows. And if you look at the midplane, actually, you can see a radial shadow in the gas and dust temperature in the midplane. in the disk atmosphere, when you look at, I guess this is the dust temperature right now. You look at the atmosphere, what happens is material from the disk atmosphere goes down to the circumplanetary region, sort of clears away, and it allows material to beam through over here in the upper atmosphere. But then when that material accumulates near the planet and the circumplanetary disk, the material, I guess, it blocks the streaming of radiation outward in the midplane. And yeah, here's the dust temperature, here's the gas temperature. Like I was saying, if you assume the dust and the gas were perfectly coupled, you would not see these thermal spirals in the upper atmosphere. This observationally relevant feature is completely washed out. Now let's talk about accretion luminosity. I tested two different ones. This is a fairly high value, of course, compared with 0. I wanted to bracket the range of possible accretion luminosities that planets could have. So now when you have these very high accretion luminosities, actually you get a much stronger planet-driven spiral, particularly in the upper atmosphere. You also get, I think, because there's more accumulation of material and sort of forms, because it blocks a wider radius or range of the disk, the circumplanetary region is quite large over here. You see shadow, a more prominent shadow, and changes in the illumination in the upper atmosphere. And then, of course, when you look at the temperature spiral, also again, quite a lot stronger in the atmosphere. And another interesting thing when you include planetary accretion luminosity is it changes the way the circumplanetary flows take place. Normally, when you have no, just a non-luminous planet, material flows into the circumplanetary region from the poles, is expelled out through the midplane. This is, I think, well established from many simulations, nothing new. When you include accretion luminosity, you basically changes the geometry of accretion. You can see it's, instead of coming in from the poles, it's coming in from 30 degrees outward or something like that. What the implications of this are for observations or for planet composition, pebble delivery, whatnot, I don't know, but it's something potentially interesting to investigate. And now, because you have because you have a bigger circumplanetary region that's extending to the upper disk, you also block more radiation, and the region behind your planet becomes cooler. This is the shadow that I was talking about.
Sorry, could you explain what's the temperature you're showing here? Is this dust temperature or the gas temperature?
I think this is gas temperature.
Yes. Okay.
Yes. Now, I mean, if you want to look at just some observational implications, I didn't go in this case all the way and do some radiative transfer calculations since it's still early in the evolution of these spirals. But I felt, it would still be helpful to provide some kind of product to compare. I picked the 3 most relevant cases, Saturn mass with accretion, and Jupiter mass. Neptune mass planets are too small to really make a major observational impact, I think. And I also looked at a higher layer than the ones that I've shown you earlier. So basically a theta of Z over R, 0.3, so about 4 scale heights above the midplane. If you look at Saturn spirals, they're clear, but they're fairly weak throughout the midplane. Sorry, this I think velocity scale is not clearly visible, but it ranges from -150 to 150, I guess, meters per second, sky projected. Or projected along the line of sight, yeah. And this is the thermal spiral, and this is the temperature spiral from plus to -5 Kelvin. If you include the Saturn mass plus accretion case, you see the spiral pattern becomes a little bit stronger and, more importantly, extends for greater duration or greater length throughout the disk. If you look at the temperature spiral, it looks almost like a peppermint candy. And if you have a Jupiter mass case, really spirals are stronger, but they don't extend for longer because they shock very quickly. And what's most prominent here are the circumplanetary flows. That's really what's giving your kinematic signature. And the temperature structure is just kind of chaos. Now,
Sorry.
yes,
What about the Jupiter mass case with accretion?
I didn't test that. These are expensive.
Was there a reason?
These are expensive. So, but I did spend some expense on looking at the long-term outcome of disk-planet interaction. So for this final study, which was very recently accepted, I tested. Okay, I'll talk more about it later, but let's take a step back to some more observational background here. I think it would help. So just focusing, someone else have a question? Okay, just focusing on the near infrared aspects of what I mentioned. Now you can see there are many disks that have been uncovered with spiral substructure, for instance, MWC758, B1247 Ori, etc., etc. I should have also mentioned there are many disks observed with shadows because that will become important shortly. And disk-planet interaction has been proposed as a potential cause of these. Now, like I mentioned earlier, there's the classical picture, Goldreich and Tremaine, planetary gravity excites waves at Lindblad resonances, etc., etc. And in particular, what this theory tells us is that M equals 2, I guess, two-arm spirals are prominent when you're considering the region of the disk interior to the planet. And if you have a very high mass planet, what's most prominent are these two-arm spirals. And if you see, for instance, V1247 Ori, there's a very prominent two-arm spiral. So the theory went basically that what we see in systems, V1247 Ori, MWC758, that it's consistent with driving by some very large multi-Jupiter mass planet that can excite this strong secondary spiral in the inner disk. But nowadays, there's some problems with this. First of all, it's, I think, a bit of a challenge for planet formation theory to explain how you can have such a high mass planet in the outer disk, particularly outside of any substructures. So where you presume all the dust maybe drifted inward before it could form something so massive. Otherwise, if there has a planet had formed out of that dust, maybe there would be some remaining outside. And secondly, if you're just looking at observations, in MWC758, I think there is some evidence in the direction of potentially a massive driver in these systems. Look at this paper. But if you look at, say, SAO 206462, now that we have JWST, people have been looking for these massive drivers of M equals 2 spirals interior to them. And these searches haven't turned up anything conclusive, I have to say. V1247 Ori, it's also an interesting case. No one has looked for an external massive companion there yet, to my knowledge. But there's also the presence of this inner ring, which is not necessarily which is not something that could be created by a multi-Jupiter mass companion. So potentially a contradiction in terms, unless you were able to find something further out. Now, this is a problem I wanted to look at with my 3-temperature scheme. So in this, for this project, I basically paired it back, didn't run the full set of schemes. I just tested beta cooling and 3 temperatures, Saturn mass and Jupiter mass. And I ran, other than that, I ran very similar simulations to what I showed you earlier, to 1000 orbits, but I did it at lower resolution in order to even be able to reach that. Even at that resolution, it took months. And then finally, in this case, now that I had a disk where the gap had fully developed, I used RadMC3D, some radiative transfer tool, to post-process and make some images. Now, if you use the 3-temperature scheme, what happens is you get asymmetries developing at the outer gap edge. And these, in turn, because they create a pressure gradient, especially in the upper atmosphere, tend to launch strong spirals in the disk. And in the disk midplane, these asymmetries, these pressure gradients are fairly weak, but in the upper atmosphere, they can become quite strong.
It's 12:30.
It's 12:30. Okay. And here's a plot of the density. You can see with the beta cooling scheme, it's fairly similar to a classical picture of disk-planet interaction. Planet carves a gap in the disk. And this deposits angular momentum. Material inward to you, I guess, loses angular momentum. Material outward gains angular momentum, and you carve a gap. In this three temperatures, you get, I think, something similar in the midplane, but then in the upper atmosphere, these asymmetries become more prominent. They couple with the radiation, become even more prominent, and then you start seeing these spiral structures. There is some depletion here, which is the consequence of, these spirals ended up including strong vertical flows, which I didn't expect. So over time, they end up depleting this outer disk. How physical that is, I don't know, but I've tested both boundary conditions, like a very hard cap, also, fairly open cap, and it seems that, both of them end up reproducing these spirals. In fact, they're stronger when you sort of contain all the material in the disk. But I digress. Basically, instabilities at the outer gap edge couple to illumination, and they break down axis symmetry and midplane symmetry in the disk to an extent, and then you get these strong spirals. And what this actually ended up resembling is if you put in a prescribed temperature structure with slight asymmetries about the midplane, slight asymmetries in azimuth in the temperature structure, you end up reproducing spirals similar to what we observe, especially if you look at these inner spirals. And if you have beta cooling to some axisymmetric initial condition, you cannot capture this effect. Yes, I guess in this case, it is beta cooling to a non-axisymmetric initial condition. But the point with free temperature is that this, azimuthal asymmetry developed naturally as a consequence of disk-planar interaction. It wasn't something that we put in. So I did some NIR image modeling, and you can see basically looking at near infrared with beta cooling, again, just ring gap, nothing too out of the ordinary, but in the upper, when you have three temperatures and you get this non-axisymmetry, you do get two arm spirals. And the brightness contrasts, end up being something like a factor of 4 or so when you have three temperatures, but much lower when you just have beta cooling. So the classical planetary Lindblad spirals for the lower mass planets we choose here are not really capable of creating strong non-axisymmetry, and higher mass planets, which could create these strong contrasts with just Lindblad spirals, are, not necessarily supported by the observations. So I think that, this is something that still definitely needs a lot of work done on it, a lot of testing with different radiative transfer methods, higher resolution, etc. But it's something that I think could be an interesting hypothesis for the formation of these multi-arm spirals without needing these massive multi-Jupiter mass planets. Now, I think just to conclude some big takeaways from this talk. So if you have three temperature radiation hydrodynamics, the scheme I developed, you can self-consistently model the disk thermal structure and the evolution of thermal structure by the interaction of gas, dust, and radiation. And then what we learned from the spiral project is gas grain thermal relaxation is essential to forming temperature spirals in the upper atmospheres of disks. And radiation hydrodynamics is needed if you want to include accretion luminosity from the planet and self-consistently model the transport of radiation from this one injection point. So in order to account for both of these things, a three-temperature scheme is immensely helpful in studies of disk-planet interaction if you want to reproduce observations. And now, interaction between disk structure and radiation can itself drive disk substructure. And, potentially it's interesting to look at if maybe some of the substructures we observe might be non-planetary in nature, rather than putting a planet next to every single substructure. So that's my talk, and I welcome any questions that you might have at this point.
Great talk. I have actually a lot of questions, but I'll start with that. One, what are you doing for dust dynamics? Is it just a fixed dust to gas ratio?
Yeah, for now we're doing that.
And then I guess another question I had, do you have any evidence that like the reduced speed of light approximation is not impacting these results at all, or?
So for the last one, I tested a lot of different parameters. That was one of them. Every boundary condition, reduced speed of light, all this stuff, I couldn't get rid of it, so. I've tested this. Yes, or I guess you're the moderator.
Brittany.
I had a question about, does the, size and extent of the grain distribution change with whatever near-infrared band? I think I missed which near-infrared band specifically you're modeling.
Oh, sorry, I think H-band.
H-band, okay. So is it significantly different over like 1 to like 2.5 microns, or is it mainly just a difference with the grains and the gas that you visually see the difference in the?
Wait, I'm not sure I quite gather what.
I guess I'm curious, is there a detectable difference in grain density? To my limited understanding of this, certain wavelengths are sensitive to different grain populations.
Yeah,
And so I was curious if it was different or the same across most of the near infrared.
I think I made one K-band or J-band, I forget, just for some proposal, but I didn't, I haven't done a systematics today. I didn't look at all of the, different frequencies. But maybe that would be interesting to look at perhaps in the future. And I should be clear, I didn't test different grain size distributions. I just have one size distribution, which I used for the thermodynamics. Yeah, size distribution, opacities, etc. I use that to compute coupling times and frequency integrated opacities. And I use the same for these radiation transfer post-processing calculations. So yeah, different grain populations is not something I've tested yet.
Yeah, I'm actually quite interested in how you actually set up the density distributions. For instance, from the masses comparing the gas and dust, I assume you have like a gas mass ratio that you set up. But for like considering the dust settlings, how are you setting up the small grains and large grains?
I think that's sort of the caveat of these things. There's only one, okay, I mean, we have a size distribution, but we assume they're all well coupled kinetically to the dust.
Yes.
We don't have independent grain dynamics yet. That's a project of future interest for me. But that would take some effort. So in this case, I don't do any settling calculation. I think, in fact, what we do is we use the same M1 scheme, and I think just alternate calculations of hydrostatic equilibrium and temperature. So yeah, that's the way it's done. There's no separate settling here yet.
And I have another question. That's
Yes.
From your simulations, it seems like if there's any planet and disk interactions, and it's very easy to create spiral-like structures from these 3D simulations in the like the scatter light image in H-band. But if we observe any of those disks that doesn't have any evidence of the spiral arms, then can we comfortably say that it seems not to have a planet?
No, I think it depends on your, depends on your planet mass. What happens in these simulations is if you don't have you have a very low mass planet, or really not a deep enough gap, then you don't see this thing. But if you have a deep enough gap, then you start seeing these interactions because a certain part of your disk gets exposed, etc. But I think, now that I think about it, tying your two questions together, what could also impact, the appearance of these spirals could be something, related to settling. Because if you have a well-settled grain distribution, you have a very long coupling time between dust and gas. And if you have that, and I guess the layers of the disk that get impacted by starlight, and if you have that very long coupling time, then okay, maybe you get some initial asymmetry, but the gas would pass through it, completely unaware because the coupling time is so long. So this could also maybe make statements about the planet mass with cooling into this presence or absence of spirals.
Thank you.
one second. Are there any questions online before we have more questions in the room?
So this might reflect my limited understanding of the field, but if I understand correctly, in the two temperature scheme, you have a temperature for radiation and then you assume a single temperature for gas and dust. Whereas the scheme that you are trying to put forward, you have three independent temperatures for radiation, gas and dust.
That's right.
If I understand correctly, a protoplanetary disk, that's a highly collisional system, and there are collisions between gas and dust which are constantly happening.
Yeah.
So since there is a lot of transfer of energy or angular momentum, possibly heat between all sorts of entities that make up a protoplanetary disk, why should we how valid is an assumption of a independent temperature for the gas and dust?
I think, 1 second. It's a good question, and I think it's exactly as valid as this plot says. I mean, again, it depends on your grain size distribution, but if you, in your disk midplane, yeah, you know, on any time scale relevant, for instance, planet formation, your dust and gas temperatures are more or less perfectly coupled. You have, yeah, in 1% of a dynamical time, any difference in the temperatures will be equilibrated, is what this is. Beta dg equals 10 to the -2 is saying. If you go to the atmosphere, then, you know, beta dg 10 to the 0, that means it takes 1 dynamical time for temperature differences to equilibrate. And if you have a more depleted settled dust distribution, like let's say, so what I have is 1% dust, of which I assume 10% is small grains that are well coupled, which supply most of the cooling, etc. Now, what if I have a more settled dust distribution that's like, you know, 1% dust, of which 1% is small grains that, you know, help cool efficiently. Then you'd multiply all this stuff by 10. And, you know, really, then the lack of collisions between dust and gas will start to matter strongly, and you'll get these very nice thermal spirals, because you'll get heat, you know, adiabatic compression and expansion of the dust and gas planet passing by, nice spirals, but there'd be no way for these to really lose energy and equilibrate with the radiation field because the collision times are so long. So you're right, there are some circumstances in which it matters, others in which not so much.
Yes.
Right, really nice talk. You showed spirals being really strong features here, but did you see any hydrodynamic instabilities developing?
I think I picked a viscosity 10 to the -3 and everything. So no, I didn't. But that's just because I killed them, not because they don't exist.
Okay, so because it's viscous, there's no like forces.
Yeah,
Triggered.
I think also, you know, 10 or even for the, you know, 5 cells per Fahrenheit for the for the long-term integrations, I think it's not something where you'd expect to see, like, you know, streaming instability or VSI or anything like that. It's just not well resolved enough. That is an interesting exercise, but it's just crazy expensive.
Maybe another related question is that, did you do I don't know, parameter search in viscosity or aspect ratio, because these things also affect, you know, spirals?
If I had more computing time, I would do anything you ask me.
Okay. And, oh, sorry. Okay. So your last point about substructures on the planets.
Mhm.
Maybe I missed it. Were you alluding to the thermal shadowing instability, or
Thermal shadowing, what do you mean?
like the atmosphere could have a staircase?
I mean, okay, so this stuff, I think, I don't really understand it. I wrote a paper on it because I kept seeing it and I couldn't make it go away no matter what. So I think there might be something to it. I think it may have something to do with, you know, that sort of stuff, self-shadowing instability. It may be related, but I have to admit I'm not an expert on the analytical theory of this stuff, so I don't know, but yeah, this could be a potential, something capable of creating substructures. I think there is work that goes back and forth on this, but it's something that I think to really answer, you need these, big, I think there has to be more work done on this, also more work done with really the top of the line radiative transfer techniques of the short characteristics or discrete ordinates. So, yeah, I think it's something that I don't think it's settled what exactly to do it, but it's something that should be looked at.
Thanks. So you saw shadowing produce a temperature gradient in the midplane of the planet, like there's like a colder exterior.
You mean like?
Yeah, there was some plot.
Yeah, there.
Yeah, like.
Okay, yeah, sure.
Does that temperature gradient drive an asymmetric radial flow? Or do you think this like has any effects on sort of the gas dynamics or?
I think on this time scale of 10 orbits, I don't think so, but there are, this guy Alexandros Ziampas, whose paper I mentioned, I think he is working on something in the direction of seeing how maybe these bipolar, like, it's monopolar, but these bipolar shadows in this case can affect the disk over the very, very long term. And I think he does see in his 2D radiation simulation some, formation of rings and gaps and all that, but it's not out yet. They're still working on it, so I shouldn't say more.
Yeah, I was wondering if I had a difficult time understanding what's going on here, just because there's a lot going on. There's heating, there's shadowing. Is it shadowing of the planet, of the starlight, of both?
So
why are some regions heated and other regions cool?
So in the midplane, you have accumulation, I guess specializing just looking over here, but also at the bottom, you have material from the atmosphere, and I think really the whole disk column basically coming down, coalescing around your planet. And if you look at these distances for the grain size distribution we use, etc., it turns out that it's sort of marginally optically thin in the midplane. The transport of radiations, there is some outward transport. It's not really diffusion like you would get in the innermost few AU. So you do end up, accumulating a lot of material, blocking the outward transport of radiation and creating this sort of shadow. But in the upper atmosphere, because you've depleted material, this is, just looking really, over here, the temperature is governed by the stellar irradiation, which we ray trace directly. And some of it is, and because you've cleared that material above the planet, it's just easier for it to shine through, and you get this bright lane. And this is something even when I did beta cooling and then post-processing, I've seen these bright lanes as well.
So I guess, I guess focusing on maybe the midplane plots first. So it looks like you turn on the planetary accretion luminosity.
Yeah.
And that creates a bit of heating in the inner disk, but then a lot of cooling in the outer disk.
I think here's one thing I have to say. I think there is a bigger circumplanetary region over here, but I have to admit part of it maybe also M1 because because it assumes radiation is a fluid, you cannot have beam crossing over here. So so I think there is a bigger shadow, but to some extent potentially artificially enhanced by the radiation going outward, sort of blocking the radiation. Sorry, the radiation going inward from the planet blocking the radiation going outward.
Okay, so by shadowing, you don't mean shadowing of the starlight, you just mean shadowing of whatever's going on locally.
I think it's not the direct stellar illumination. I think it's a thermalized radiation in the midpoint. And
what are the optical depths in each of these sort of simulations? Like is it or I guess the vertical optical depth, like the
vertical
boundary to the midplane.
So 40 AU, 200 5. Maybe I don't know. See 200
or where does tau equal 1?
Tau equals You mean the vertical tau equals one surface?
Yeah,
I don't think I really looked at, I don't think I looked at that for this, but I'd say at most a few vertically.
scale heights.
No, I'm saying the integrated.
Oh, the
optical
total
tau-
integrated.
Yeah.
Okay.
I guess it should be the position where the gas and dust temperature decoupled, right?
And I think
So
this,
I remember you have a plot somewhere in the.
oh, you mean, but this, yeah, but I think this is a little, this is
Okay.
for the radial tau equals one surface where,
Okay,
but yeah, I see what you mean over here. There's, this region over here, which seems, just optically thin free streaming from the star. But then I think the transport of thermalized radiation is something else entirely.
Okay, are there any more questions online? All right, I'm going to cut off the question session there, but thank you all for a wonderful discussion. Thank you to Dhruv for a great talk. And if you would like to talk to Dhruv more while he's here, he will be here until end of day Thursday,
Yes.
end of the day Thursday. And you can get in touch with him directly or sign up on the sheet that I sent out. So thank you all for coming.